All right, so welcome back to another lecture of Statistics 568, Design and Analysis of Experiments. We are not done with multiple testing corrections. Today, we're going to be going one step further and find more sophisticated modern ways to do multiple testing. Let's go look at that. So last time we talked about the family-wise error rate. Today we're going to go into a more modern method known as the false discovery rate. It's a little bit more sophisticated. It's going to take a little bit more work to get at, but it's going to give us a much more powerful way to do multiple testing correction, especially when the number of hypotheses get to really, really high. So let's see if we can figure out how to do this. And we're back with another lecture of Statistics 568, Design and Analysis of Experiments. Today is going to be part 2 of our multiple testing lectures. It's the only extra part we're going to do. We're going to be done after today. And we're going to extend what we did from the last lecture. So in the last lecture, we looked at the family-wise error rate. And again, that's trying to control the probability that we get at least one false positive among multiple tests. Today, we're going to do something a little bit different. We'll be looking at the false discovery rate, which is the percentage of false rejections among all of the rejected hypotheses. So if you reject, say, 100 null hypotheses and the false discovery rate is 10%, then that's claiming that on average you'd have about 10 of those would be false rejections, the other 90 would be true rejections. So as you might intuitively imagine, this will give us a less strict criterion for multiple testing correction. What it means is we're going to be allowed to keep, or I should say, we're going to be allowed to reject more null hypotheses among our tests, which is another reason why people like it a lot. Right, so let's get into that. And just to recap from last time. So last time, we did the FWER, or the family-wise error rate. And we talked about different methods. We talked about Bonferroni. We talked about Sidak's method. We talked about Holmes' method. And more generally, we talked about the step-down. I didn't mention it because there wasn't much to mention, but there is also a step-up method. Remember, step-down starts with the most significant, that is the smallest p-value, decides whether or not to reject it, and then goes to the next smallest, and the next smallest working its way up. The step-up method, again, terrible terminology, starts with the largest p-value, and then starts to work its way down the list from the most, or the least significant to the most significant, from the biggest p-value to the smallest p-value. So I'll say step up or step down / up. And there are some finer points to one versus the other, but we're not going to get into that now because we eventually want to get back to more experimental designs, but I still think this is a good, a worthy diversion. So now what we're going to do is we're going to consider the FDR, or the false discovery rate. And the easiest way, I think, to understand what's going on is to draw a table. Before we get into actually trying to control the false discovery rate, we have to understand what the false discovery rate actually is. So let's say we have M hypothesis tests, as we did last time. And with all those hypothesis tests, we have that M naught are where the null is true. Well, I'll just say are true nulls. Again, it's just easier in English to write it that way. And M1 are true, I'll say alts for alternatives. And of course, M1 plus M naught is equal to M, right? Because we sum up, we've basically taken our M hypothesis tests and we've broken them into two sets. The ones where the null is the truth and the ones where the alternative is the truth. And what we can do with this, let's get rid of that FWER because we don't need it anymore. We got something better. Yes, and we also need R, which is going to be the number of rejected nulls. So I'll put that over here. And R is the number of rejected nulls. Okay, and then what we can get is we can get a table. And the table we're going to have, we'll say true null, and we're going to have true alt. Okay. And then on the for the columns, let's make that a better straight line. For the columns, we're going to have the decided or chosen. Basically, what did our test say? I didn't write that right, spell that right. Decided null or decided alt. So basically, did our test say that we should reject the null in favor of our alternative, or did it say we should not reject the null? And then just to make the language simpler, we'll just say the null is true or the alternative is true, even though if we really want to be pedantic statisticians, we would say that we failed to reject the null rather than claiming the null to be true. So you might get some pedantic statisticians who get mad at you if you say accept the null hypothesis. But in the language of false discovery rate, it's just so much easier to say it that way rather than a bunch of double negatives floating around everywhere. Anyway, the idea is that, well, we know that we're going to reject R, which is down here of these hypotheses, and M minus R have been failed to reject, and the total sample size is going to be M. Now, we know that there are M naught true nulls and M1 true alternatives. So then we're going to use the notation A and B. So of the R rejections that we have, A of them are going to be false rejections, B of them are going to be true rejections. Actually, I'll put that in after I write the other bit. And to make the table sum up correctly, we're going to have M naught minus A and M1 minus B. So what this table actually is telling us is that we have, this is a true negative. This next one would be a false positive, right? Yeah. A false positive. It's something that we reject where we weren't supposed to reject. The opposite corner is going to be a false negative. We failed to reject when we should have. And then the bottom right is going to be the true positive, which is we correctly rejected our null hypothesis. So this is just a table. You've probably seen this before in another stats course, but it's good to have all this notation in our heads, because now we can very quickly define what the family-wise error rate is and what the false discovery rate is. So in this notation, we get that the family-wise error rate becomes, well, two things. It's the probability that A is greater than 0, right? It's the probability of at least one false positive. So we're basically saying what's the probability that A is larger than 0? At least one or more of the nulls were falsely rejected. Now, as an expectation, we can write this as the expected value of A divided by M naught. So in this case, we're just saying it's the number of false rejections divided by the total number of nulls that we weren't supposed to reject, right? So that's the idea of what the family-wise error rate is. You can think of it as this expectation. or also as a probability statement. Now, for the false discovery rate, we have something that looks almost the same, but we're changing the denominator. What we're going to say is that now we're going to have A, the number of false rejections, but we're going to divide by R, the total number of rejections. And mathematically, things become a little bit trickier because M naught in our nice parametric statistical, not parametric, or what am I trying to say? Frequentist statistical setting, right? We would think M naught is fixed. We don't know what M naught is a priori, but we would treat it as saying that, okay, I ran my M experiments. Some set of those are the data is coming from our null hypothesis. And some set of those, the data is coming from our alternative hypothesis. So in this case, we think, okay, M naught is going to be some fixed unknown. A is going to be random because it's dependent on the data, right? M naught is dependent on the universe in some sense. It's dependent on the ground truth of the world. But A is random. It's dependent on the data. Depending on what the data is, we may reject more or less or fewer of the null hypotheses that we weren't supposed to reject. And if we repeated this experiment again, M naught wouldn't change, but A very well could, depending on the newly collected data. Now that's in contrast to over here, where both of these, A and R, are both data dependent, which is i.e. random. Which means we have to work a little bit harder, because if something's M naught is not random, we don't even have to worry about the expected value of it unless we decide to be Bayesian. But in this case, we have that both the number of false rejections and the total number of rejections are both random variables that we have to figure out how to deal with. So mathematically, this is a bit trickier. And yeah, basically, well, I don't know the whole history of the false discovery rate, so maybe people were working on it before 1995. But in 1995, the famous Benjamini-Hochberg method was published. And as I noted in my lecture notes when I wrote them back, I forget, a couple years ago, it had over 50,000 citations in Google Scholar. So yeah, they're doing pretty well with that paper, gotta say. Maybe we can go check that at the end and just see exactly how many citations they have. All right, so what we're going to talk about now is the famous Benjamini-Hochberg method for controlling the false discovery rate, which was published in 1995 and still getting tons and tons of citations. Though eventually I feel like the only next step for a paper after getting tens of thousands of citations is to get none, because it becomes such ingrained part of the science that nobody even bothers to cite it anymore. Much like the F test, nobody cites Netacor, or Tukey's test, nobody actually cites Tukey. They just say it is what it is. But anyway, yes, so now that we have that, the question is, well, what is the Benjamini-Hochberg method? So as before, we need to order our p-value. So first, we need to order the p-values. And we get, once again, that p1 less than or equal to p in parentheses 2, all the way up to pm. So all I'm doing is reordering the p-values in increasing order. And then so first we order the p-values. That's step one. Next is choose an FDR Q in 0, 1. Now, we use the notation Q and not alpha, because alpha, we always go back and think it's like the test size or the probability of a false positive. Here we're doing something different. We're not looking at that anymore. And the notation, at least in some of the references I saw, was Q. So we'll stick with that. And then we find the largest I'll say in from 1 to m, such that what? The largest I such that p I is less than or equal to I divided by m times q. But I'm pretty sure, yeah, then we reject all and reject all h naught j such that j is less than or equal to I. Okay. Yeah, so that's roughly the idea. It's going to look a lot like what we did with Holmes' method, except if you notice there's an I in the numerator instead of in the denominator. So I'll put off to the side here. Recall that Holmes said to reject if pi is less than or equal to alpha divided by m minus I plus 1. So in this case, the threshold is actually a lot larger. It's more liberal. It will reject more null hypotheses. Also, Q and alpha would be set separately. Again, much like setting a false positive or a family-wise error rate alpha or a test size alpha, whatever you want to call it, you still have to think about now, what do I want Q to be? In the textbooks, you sometimes see them say 10% or 5%. There's no real right or wrong answer. I mean, there's probably plenty of wrong answers, like 1. You don't want to set it to be 1, because then what's the point? But otherwise, there's not a lot of wrong answers that you can do for Q. You just need to choose a good value for it. And then depending on how big or small, you're either going to reject more or fewer hypotheses. All right, so this leads us to a theorem, and it's always a good day when we get to do a theorem. So the theorem from Benjamini and Hochberg's work says that, well, okay, given the m-ordered p-values above, assuming that the pi are independent for those I corresponding to true nulls. Basically, we don't need all the p-values to be independent. We just need the p-values coming from null hypotheses to be independent. So slightly weaker, still kind of a strong condition. It would work in our cases. For most of the designed experiments that we would look at in this course, not always going to be true in general. Regardless, given that we have that independence condition, then the claim is that the false discovery rate, which is equal to the expected value of A divided by R, as noted above in that table, is going to equal pi naught times Q, which is less than or equal to Q because pi naught is going to be the number of nulls that are true divided by the total. So this is really just the fraction of true nulls. Recall that I naught divided by m shows up a lot when we were looking at the family-wise error rate as well. It showed up in Bonferroni, for example. It showed up in the exponent in Sidak's method. So in this case, yeah, it's going to show up. It shows up a lot. And what it means is that the more, in some sense, the more true null hypotheses among the tests you're running, the more efficient the method is. Whereas if you really are supposed to be rejecting a lot of the hypotheses, then these methods will probably miss some of them. They'll be less efficient in the sense that they will probably fail to reject everything that you want to reject. I think not always, right? But very often when you're testing lots of hypotheses, you're going to assume that most of them are not significant and only a few of them are. It's kind of like a needle in a haystack. You're trying to find which of your tests are significant, and you kind of assume that most are not. We're going to talk about this more when we get to factorial designs, because when we do factorial designs, we're going to be testing 2 to the whatever hypotheses, and the assumption is that one of the main assumptions in that section is sparsity, in the sense that we assume that most of the effects are not interesting and only a few of them are. So at least in that case, our pi naught would be close to 1, because we assume that I naught is close to m, if that kind of makes sense. All right, so anyway, that was the theorem. It just basically says, so roughly it says the Benjamini-Hochberg method works. It controls the family or false discovery rate. So then the question is, well, why? And yeah, we should probably prove that. It's kind of a fun little proof. It even gets to use martingales, which you may or may not, probably not have seen unless you spent a lot of time doing probability theory. But it's still kind of fun to look at anyway. So we're going to do that now. All right, so let's prove this theorem. And again, I'm not going to be testing you on the finer details of the proof, but I think it is still very good for your learning to go through and try to understand it. So the first thing we need to do is say for some t in 0 to 1, we're going to say let RT be the total number of p-values less than t. Let's put that on the next line so we'll say RT is equal to the number of pi that are less than, I just said less than t. It's not going to matter, I guess, if they're, it's continuous, so we're probably fine. All right, so it's just the number of p-values that are less than t. If I pick, some value of t in 0, 1, I'm just counting how many p-values are less than t. And we're also going to have an AT. So you can think of, right, RT as if I set a threshold for rejection, like if I set t to be 5%, then RT is the number of hypotheses rejected that are the number of p-values that are less than 5%, or the number of nulls that I would reject if the test size were 5%, say, for example. Now, AT is the same thing, but it's the number of p-values from null hypotheses, the number of pi less than t, I'll say, such that I is in I naught. This would be like the number of rejections at test size t, and this guy would be the number of false rejections at test size t. Cool. So that's basically taking the A and the R above and now indexing it, or I guess giving it some argument T. that we can work with. All right, so we have that. So then we have to define the false discovery proportion. So the FDP, or false discovery proportion, is just going to be A over R, or in our case, we need to just modify it slightly, or I'll say more precisely, the false discovery proportion is going to be, in this case, AT, as a function of T. It's going to be AT divided by the max of RT and 1. Basically, we do this so we don't divide by 0, right? Because if we don't put that max in there, we could choose T smaller than the smallest p-value, in which case we get 0 divided by 0. That's never a good time in math. So almost never a good time in math to have 0 divided by 0. So we want to skip that. We don't want that. So we put a max in. Now, we're going to have to define more stuff. So we'll say next, we define Q. So what's capital Q? Well, capital Q of T is going to be MT divided by the max of R, T, and 1. Something that looks like that again. Again, just so that we can choose just so the denominator is never 0. Now, what is M times T? That's really just, T is just a number between 0 and 1. M is the total number of hypotheses. So you could say that, right, M times T, I'll put it off to the side here. M times T is the expected number of rejections at level, or test size, I'll keep saying at size T, if all hypotheses are, we'll say, true nulls. Basically, if all the hypotheses that we're testing, all M of them, are true nulls, then what that means is that their p-value should be IID uniform 0, 1. Now, if we want to know how many of those would randomly fall below the T threshold level, T again is like the threshold or the test size, well, approximately M times T of them, that fraction. If T is 50%, then we would expect half of our tests, M, half M over 2, or half of them to be rejected. If T is 1%, we would expect, well, 1% of M tests to be rejected. So it's the expected number of rejections divided by, well, the actual number of rejections at at index T. I'm also teaching time series, so whenever I see T as an index, I keep thinking time, so I may make that mistake again. Anyway, let's get us some more room here. Oh yeah, we also need another thing. So most of this proof is just defining a whole bunch of junk and then cramming it all together, and then magically it all just works out. Though I feel like I'm not giving them enough credit when I say that. It was pretty cool, and I still think it's pretty neat. So I definitely don't want to, shortchange them. Anyway, there's a T sub Q that we also need. Now we're going to need to have a supremum. So now things get kind of fun. It's the sup. It's the largest T, or the sup over T, because it's continuous, such that QT is less than or equal to Q. All right, so this is just a special value of T. It's the value of T where it's the largest value of T where this qt up here is less than the chosen value of q. Remember, little q is going to be the false discovery rate, the target false discovery rate chosen by the experimenter. And qt, again, is the number of expected rejections divided by the total number of rejections. And consider, yes. So because the p-values are ordered, now we'll say, because of the ordering, remember, p1 less than or equal to p2, etc. Well, we have some interesting behavior now for our function, so r. Because of this, we have that if r is evaluated at pi, what is that telling us? Well, remember r, it says it's the number of rejections at test size t. So how many p-values are less than or equal to p sub I? I think I should actually strictly make this less than. So I do need to make this strictly less than or equal to. That was an imprecision in my lecture notes there. And presumably I need the same thing for AT, because the point is, how many p-values are less than p sub I? Well, the answer is exactly I of them, right? All I'm doing is I'm coming up here to my, where is it? My ordered p-values, finding p sub I and saying, well, how many of these guys are less than or equal to p sub I? Well, there's exactly I of them because they're ordered. So that's easy. And that's kind of nice. Now for Q, we can actually do the same thing, because if we consider, I always feel like proofs don't make sense until the very end, right? It starts off and it's just like, why in the world is he just writing all this stuff down? And then at the end, all the terms kind of rearrange and everything works out nicely. But we haven't gotten there yet, so just kind of stick with me. If we put pi into q, we get this basically, right? Because the denominator becomes r evaluated at pi, so we're just taking this guy and shoving him in the denominator, and the t in the numerator is now set to p sub I. All right, so we got that. Yes, so then given all of this notation, let's see if I can keep it all on the screen here for a moment longer. Given all of this, we rewrite the, I'll call it BH rule, rejection rule. And we rewrite it to be reject H naught evaluated, or not H naught I, the ith most significant hypothesis, I guess. If P sub I is less than or equal to T sub Q. Right, so again, continuing on from here, we say under H naught I, we have that PI is going to be uniform 0, 1. So what does that mean? Therefore, the expected value of AT, remember, what is AT? It kind of fell off the top of the page. It's the number of false rejections at a given test size T. There, we can kind of get it now. I'm not going to squeeze it on the same page. So what would be the expected number of false rejections at a test size T? Well, it's the number of true nulls times T. Simply, it's just saying, well, if I have this many true nulls, they're uniform 0, 1. What's the probability that one of them is, well, not the probability, what's the expected number of them that would have at random a value, a p-value less than T? It's t times the total number. I'll say, i.e., we expect that many, or we expect t, it, p-values in the interval 0 to t. It goes back to my pick a t here. Right, we would expect about that many p-values to lie to the left of the value, the threshold t that was chosen. And now we get to have some fun with even more notation and eventually a martingale. So we have another definition. So now what we do is we define AT to be little a at t divided by t. Okay, so you're kind of just normalizing AT based on the length of the interval. AT is the number of false rejections. That is the number of p-values that lie in that interval. I'm dividing by the length of the interval. So it's, in a sense, kind of like normalizing it a bit, I guess. What it means is we have some interesting properties. We can say now, for s less than t, we have, well, a couple different things. First, we have that the expected value of AS given AT is going to equal S over T times AT. Remember, this is a conditional expectation, so we're conditioning on AT. So, okay, why would that be true? Well, what that's basically saying, let me draw the picture. Right, if we have, let's say, 0, 1, t is bigger than s. So what we're saying is, what's the expected number of false rejections? Let me get another color here. What we're saying is, what's the expected number of false rejections or p-values that lie in this interval, given that I already know how many lie in this interval. And what it is it's basically saying it's the number of p-values we have to consider, the number that lie in that interval, AT, the bigger interval, times the ratio of the lengths of the intervals. So this is kind of like a ratio of interval lengths. So what it's really saying is that, okay, if let's say S is half of T, then it's saying, well, if I have this many false rejections in this interval and I cut that interval in half, I should see half that many false rejections. And similarly, if I cut that interval by a third, I should see a third of the false rejections, and so on. So intuitively, I mean, when you write out the expected value, it looks a little bit weird, but when you think about it intuitively, it makes a lot of sense. It's just saying, if I know how many false rejections or false p, or how many p-values, let's say, lie in this red interval, then based on how much shorter the blue interval is, I can take a good guess. That is, I can look at the expected value of how many of those false p-values, or p-values, I should say, for the false rejections lie in the blue interval. There's really no such thing as a false p-value, so I have to watch that. Anyway, we have that, and we have some other things. We have that the expected value of capital A given S of S given capital A of T. Well, what's that going to be? that's just going to be the expected value of AS divided by S given AT divided by T. This is just going to be, well, it's going to be what we had above, S over T, AT, but we have to divide by that S from here. This guy is that guy. And then the S's cancel out, and we're left with just AT over T, which is just AT. So that's nice. Basically, that conditional expectation is just going to equal AT. And that's pretty good because that's hinting that we have a martingale to work with. And we have one more expectation to look at, which is that the expected value of AS given AT prime for all T prime greater than or equal to T, well, that's also just going to equal AT. Effectively, what it's saying is that if I don't just have the red interval, if I have every interval that's bigger than the red interval, like this, for all possible T prime values between 1, this would be T prime here, which can go from 1 to capital or to lowercase t. If I have all possible, I shouldn't put another interval there, it'll get confusing if it isn't already. If I have all of those, if I have information on all of those intervals, all that matters is I have basically what the smallest one is, which is the smallest value of T prime, which is T in this case. So all of this, basically, this means that AT is a martingale. Hooray, which you may or may not have ever heard of, but it's a really neat tool in probability theory. Think of it like a random walk, just a generalized version of a random walk. In this case, it's indexed by T. So typically you might have a random walk that starts at 0, and as time increases, it just kind of wiggles along, something that we would look at in, say, time series or otherwise. In this case, our martingale is kind of going backwards, though there is a backwards martingale, so I don't want to get into that. But it's the time is going from 1 to 0, or the index T, not strictly time in this case, it's actually a threshold. The threshold is going from 1 to 0. So the martingale is kind of moving from, it's kind of like a random walk from 0 or from 1 to 0. Again, not super important to know all the nitty-gritty details because I'm not expecting that everyone's seen this before, but it's kind of neat because once we have this martingale property, we can kind of just conclude really fast. So let's do that. All right, so we're back, and now we can finish this proof. So now that we know that AT is a martingale, what we can say is we can consider TQ to be a, I guess, random stopping time, or yeah, stopping time. Stopping time is a way to stop the martingale. So, for example, if you imagine a random walk dictating the price of some commodity, then you might say stop as soon as it hits a certain value. Once the price gets above whatever, $50 or below $10, stop and then do something, maybe sell or whatever. So you can think of a stopping time as a random time. We don't know when it's going to occur, but if it does, then we stop and we would typically do something. Again, the easiest would be like if you're watching the market and you say, okay, I have a random price. I don't know what it's going to do. It's going to go up. It's going to go down. It's going to wiggle all around. Once it hits a certain value, then we stop and maybe sell it off and then, either make a profit or cut our losses. In this case, we can think of TQ as a stopping time as T goes from 1 to 0. So we're going again, time, or the threshold now is going from 1 to 0 compared to, say, a standard example of a martingale where you would have time going from 0 to infinity. But a martingale nevertheless. So basically, I'll say that is TQ is the first time that QT falls below Q. Yes. So it's really just saying, I don't know when this is going to occur, but as we move T from 1 to 0, eventually QT will fall below the value Q. So again, I can draw a kind of a picture. It's not a great picture, but just to give you an idea that what is QT? Do we even remember at this point? QT is the expected number of rejections divided by the total, the actual number of rejections. So when T is equal to 1, this is M divided by M, which is just 1. When T is equal to 0, this thing goes to 0. So I don't know what this thing's going to do, but we know that, let's switch colors. We know that it starts at 1, it ends at 0, and it maybe wiggles around here. And eventually, it's going to drop below the threshold value of Q, I guess based on my drawing that occurs here, even though it wiggles back up above it. So all we're saying is we start at time or threshold 1, T is 1, we take T to 0, and as soon as QT, this squiggly blue line, drops below the red line, we stop. It may not actually look like that in practice, but this is kind of the intuition that I'm trying to get at here. Anyway, given all of that, what does that mean? Well, therefore, we can apply a fairly powerful theorem called the optional stopping theorem, which is a pretty cool tool when it comes to working with martingales. It basically says that the expected value then of our process A, if our martingale A at the stopping time, the expected value at the stopping time is just going to be the expected value of A at time, or at index T equals 1. In this case, that's just going to be the expected value of little a at 1, because big A, right, is just, well, you remember, big A is just little a divided by T. So if I divide by 1, well, it's just little a. And the expected value of this, well, we know what this is. If we set our threshold to be 1, it means we would reject all the hypotheses, and thus we would have exactly I not false rejections. All right, so we have that. That doesn't look too immediately exciting, but the neat thing is that therefore our false discovery proportion at TQ, well, what's that going to be? Let's go back and find it. It's going to be up here, AT divided by the RT, or with the max thrown in there. So what we end up with here is now ATQ divided by the max of RTQ and 1. Okay, and that we can rewrite, right? We can rewrite that in terms of capital Q. Capital Q, I always forget what everything is. I have to look it up again. Capital Q is MT divided by the max. So if we rewrite this, we can rewrite this as ATQ, and then, where is it? Capital Q, TQ divided by MTQ. So this is just using our definitions to rewrite. So far, we haven't done anything that profound. We're just rewriting the false discovery proportion given the definition of QT above. All right, now that we have that, what we can do is we can rearrange these terms, and we can note that at time Q, at index T sub Q, capital Q is just going to equal lowercase q. So I can break this into two pieces. We can have a TQ divided by TQ here, and we can have capital Q, which just becomes lowercase q divided by M. All right, and then finally, lastly, we then get that if we take the expected value of the false discovery proportion at the stopping time TQ, then what we get is well, what's the expected value? Remember, this thing here is just A at TQ, and what we said on this line is that its expected value is just I naught. So when we do all this, we end up with just simply Q I naught divided by M. And we're done because this is less than or equal to Q as desired. So like we said at the beginning, oh, and let's put the nice little QED box because that always makes me happy. It's good stuff. Yeah, so what we said at the beginning, right, is that the false discovery rate is the expected value of the false discovery proportion, and it should be given a user chosen value of Q. This is the false discovery D, false discovery rate, which is going to necessarily be less than or equal to Q, which is what we want. Now, again, if lots of null hypotheses should be rejected, then our false discovery rate will be actually a lot lower than we would like. In the case of M is large and I naught is also relatively large, then in this case, we'd have a pretty accurate value for our false discovery rate. Cool. So maybe that makes sense, maybe not. It's kind of a neat proof, I think, just because it's a nice application of Martingale theory, which when you first learn it is like, well, wait, why are we doing this? How is this going to help us? And it really kind of works out here very elegantly. But again, I'm not expecting you to be familiar with what a martingale is, so don't worry too much about that. Anyway, that's Benjamini-Hochberg. And before we're done, I do want to point out that there is a, well, I didn't write the name in my notes. Well, I'll say it out loud and then I'll probably mispronounce it. There is a follow-up, method, which is if the PIs are not independent. Because remember, at the beginning, we assumed that our p-values, at least the null p-values, were all going to be independent. That's not always the case. At least in our design of experiments course, it's usually the case if our designs are balanced. But in the case that we don't have a nice balanced design, we may not have independent p-values. And if we don't have independent p-values, we can't use Benjamini-Hochberg, but we can use the Benjamini. Now the question is, can I remember how to spell this? It's like Yekutieli, maybe, if I got that right. We'll double check when I load up R in a second to see if I actually spelled that name correctly. But it's a different method. We'll call it the BY method. And it's effectively the same thing, but works under, I'll say, like BH, but works under arbitrary, let's say arbitrary dependencies. than C's. And roughly, I mean, not roughly, the idea is that we sort of do the same thing as before. We find the max index I such that what P I is less than or equal to 1 over Cm, whatever that is, I'll tell you in a second, I over M times Q, where Cm is equal to the sum of it's a harmonic sum or series, I guess, of I to the minus 1. Then reject all H not I for, I guess I should put the parenthesis there, in there, for I less, or for J, sorry, this should be a J, for J less than or equal to I. So we do the exact same thing. We find the largest index such that this condition is met, but we have two pieces here. We have this guy, which is just Benjamini-Hochberg, and we have this guy, which is the penalty for lack of independence. So it'll be a more conservative method because Cm is going to be larger than 1. So if I divide by Cm, I'm going to shrink the threshold that Benjamini-Hochberg would give me, and thus I would reject fewer null hypotheses using this method. Of note, the harmonic sum actually diverges as m goes to infinity, so this actually would become quite bad, I would imagine, if m gets extremely large, since that series will eventually just go off to infinity. Not necessarily that fast, but fast enough that it could cause some trouble. All right, so these are the two methods, mainly the Benjamini-Hochberg, but we have the second method, which is an extension of the first one, for controlling the false discovery rate. Again, this is a nice alternative to the family-wise error rate because it will be less conservative. It'll allow us to reject more null hypotheses given the knowledge that some fraction of those rejected null hypotheses are going to be false rejections. So let's look at this in R before this lecture is over. So we're going to take a break, switch over to R, and see how this works in practice. And now we're back, and this time we're in RStudio. And what we're going to do is we are going to look at the p.adjust function. So R, in its standard base stats package, has a nice method which will do most of what we talked about, actually. It doesn't have Sidek's method now that I look at it, but we have Holmes, we have Bonferroni, we have Benjamini-Hochberg, and the BY method, which, if I double check the spelling, it's Yekutieli. I did get the IELI right, so almost correct. I apologize, though I doubt anyone associated with that paper, Benjamini or Yekutieli or otherwise, will actually be watching this video. But just in case you do, I apologize for getting your name wrong, spelling it wrong in the written portion. Regardless, now we have method that we can use to adjust the p-value. So to do that, we need some p-values. So what I'm going to do is I am going to generate, let's get a lot, right? So I'm going to say PVs, and we need two different types of p-values. We need first our null p-values, which are going to be R uniform, and we're going to, let's say, have 180 of them, 160, say. And then what we're going to do is do a random beta. And what we're going to do for our random beta is we're going to generate 40 random beta distributed random variables. And now, which way does the beta distribution go? I always forget. I think what we need is we need the first parameter to be 1 to kill off the t to the a minus 1 term. And then the other parameter we can set to be something large, like, I don't know, 6. How about that? So let's look at our p-values. Okay. Except, did I do that backwards with my, I thought the final group should be, let's see what they look like. Okay, so notice that my final group of p-values are actually smaller than my initial group. This big block here would be my my null p-values, and the latter 40 would be my alternatives. But I kind of want to make them a little bit more significant, so we'll turn 6 into 8 and run this again. There we go. So again, I have my little block here at, we'll say h is equal to 160.5. Just to give you an idea of what we're working with here. That did not work at all because I said h and I actually wanted v. There we go. So everything to the right of my gray line are supposed to be the hypotheses we'd want to reject. Everything to the left are supposed to be the null hypotheses. And if we just chose some if we just chose some threshold arbitrarily, like say 5%, because it would make Fisher happy, we end up with something like this. So these gray lines are kind of telling us it's really that table that I drew before. We have our big block here, which are going to be our true negatives, the tiny block down in the bottom right, which are going to be our true positives. Now it's going to be flipped. I think it's flipped from before. Up here, we're going to have our false negatives. And no, that's the same as before. We have our false negatives here, and we have our false positives down in the this bottom rectangle there. Okay, so what happens? Well, let's do some p adjusting, right? What we can do is we can say we can figure out how many p-values would be falsely rejected in this case. So if I say 1 to 160 and say less than 0.5, 12. So I only got 12 false rejections. That's not so bad. Or yeah, false positives. Whereas for my other case, I get 13 true rejections. So overall, it looks like I have 25 rejections, which means, well, there's a couple things. First of all, the family-wise error rate in this case would be 12. The achieved family-wise error rate would be 12 divided by my 160. So it's about 0.075. So it is greater than the 5% because I didn't do any adjusting, right? And in this case, I would have falsely rejected at a higher percentage than 5%. I rejected about 7.5% falsely, false positives. Meanwhile, the FDR achieved is actually going to be pretty close to 50%. Yeah, because it's going to be 12 divided by 25, because there are 25 points that get p-values that get rejected here, and 12 of them were falsely rejected. So that's telling me that, you know, I rejected my 25 p-values, but about half of them were false positives. So let's see what happens if we do p. We'll do pv dot Bon for Bonferroni. And then what we do is we say, let's go back to the documentation. What we need to do is say p dot adjust, give it our big group of p-values, and say, you know what, I want to be conservative today. I'm going to use the Bonferroni method. Bonferroni. And now what do I get? Well, let's plot those just because it's fun to look at them and see what we get. Okay, so now they get all up to 1. So what in the world happened here? Well, the p-adjust is not adjusting the threshold, it's adjusting the p-values. So I should have written this in my notebook, but we'll just type it out here. If I have a p-value, then what Bonferroni says is I should reject it if it's less than alpha divided by m, the total number of tests. In this case, it would be like dividing by 200 tests. But equivalently, I can move that m to the other side of the equation and say, so an equivalent way to do Bonferroni would be to take all my p-values, multiply by the number of tests, and then reject if any of those fall below the value alpha. In this case, we're not going to get a single one of those below alpha because we basically multiplied all of our p-values by 200. And of course, set a maximum, a minimum, that is, don't let it go above 1 because it doesn't make sense to go above 1. So basically, in this case, all of our p-values get set to 1, except for a very few, but they're still quite large. So what we would do in practice, again, this didn't, Bonferroni killed us here, but what we would do is we would take our p-values and say, okay, these are my adjusted p-values. How many of them are less than, which ones are less than 5%? Well, none of them are less than 5%. So we don't do any rejection. So that's disappointing. And a good reason why we wouldn't want to necessarily use Bonferroni's method. But still, it works in very general settings. So yeah, you can, you got to sort of use it when you need it. But let's try something better, right? Well, we have Holmes' method. That's the step-down Bonferroni. So let's see if that gets us anything better, because Bonferroni was way too, we'll just say HM for Holmes. Home. I thought it was Holmes with an S. Holmes's method. I should double check that because here it's just Holme, Holme, without the S. Always try to get people's name right, even though I typically always get them wrong. Okay, so Holmes' method did kind of the same thing as Bonferroni in this case. We didn't do very well, so that's no good. We're still not going to get any rejections in this case. I think everything else is, some of it's just overlap. I believe Hochberg is, let me double check. Yeah, there is a Hochberg method. Honestly, off the top of my head, I forget what it is. I'd have to go look it up. But we can do the BH or the Benjamini-Hochberg method. So let's try that. This is just going to be an advertisement for false discovery rate control, isn't it? Because both our Bonferroni and our Holmes method failed miserably to reject anything. Let's see if, oh, capitalized. It's case sensitive. All right, let's see if this does any better. Okay, so at least in this case, we didn't have them all being set to 1. Now, they're still quite high, if you notice, but we have a different interpretation here. We could set the false discovery rate to be, say, 20%. I think I made this problem too hard for the poor multiple testing corrections, but you got to make them work a little bit. If we set our, actually, what is the smallest value there? It looks like it's a little bit above 20. It's 20.7, okay. So yeah, if we say set our false discovery rate to be 21%, say, oh, I don't want that. I want to sum it so I see how many things would we reject. Well, we'd reject 4 hypotheses, and we would claim that approximately 21%, maybe I should set 20 to 5. It's going to be the same thing, but it's easier to interpret. So let's say we set the false discovery rate to be 25%. Then given this simulated data, we would reject only 4 of our hypotheses with the assumption that on average, like if we repeated this many, many times, approximately a quarter, or one of them, would be a false rejection, and 3 of them would be a true rejection. But remember, this is on average. If we actually look at our data here, we see that 2 of them are false rejections, and 2 of them, this one's on the border, actually. I don't even know where that one is. So let's see. Yes, so good. So we had 2 false rejections, and we had 2 true rejections. Now, presumably, if we believe that the Benjamini-Hochberg method works, then if we were to repeat this simulation over and over and over again, we should see on average 1 false rejection and 3 true rejections, again on average, but not in every individual case. Like in this case, it was 50-50. Okay, and then lastly, we can do the Benjamini-Yekutieli method. If we switch this to by and this to be capital Y. Of course, that's just a more conservative method, so it's just going to make life harder for us, I think. Yeah, and sure enough, it set everything to be 1. So it looks like I'm being a bit unfair. Maybe I didn't make those other p-values small enough to be detectable. So while we're at it, I've got as much time as you got, as much time as we need. So let's go back to where I generated our data, and let's just make this much more absurd and set our alternative hypotheses to have a beta parameter of 32. Okay, now we have a nice tight little cluster down here. So let's see if we can get some better results with any of these methods, because my significant tests, my significant p-values were not really significant enough to get anything interesting going on. So let's go back and look at Bonferroni and see if Bonferroni is going to give us anything. Okay, it looks like we actually got a rejection with Bonferroni. Hooray. So again, what we would do is we would choose an alpha, a family-wise error rate, and basically say which hypotheses, which adjusted p-values are less than, say, 5%. And one of them is, it's a true rejection, so that's nice. So we got one. That actually is significant with Bonferroni with a family-wise error rate of 5%. Let's try that again with HM, the Holm. Holm should do something slightly different than Bonferroni, but for some reason it was giving me the exact same thing here, so I'm kind of wondering about that. Okay, it did adjust it ever so slightly, if you notice. It just didn't do a very good job. As I go between Bonferroni, Holm, Bonferroni, Holmes, right? It adjusted ever so slightly, but doesn't really do anything that significantly different. We can try the Hochberg method. I actually forget what the Hochberg method is. I'd have to go look it up. We'll say HCH, or yeah, for Hochberg. All right, so that one also does about the exact same thing as these other methods. In fact, it looks identical to Holmes in the p-values that it returned without looking at them in finer detail. But we can definitely do the more interesting family or false discovery rate methods that everyone loves these days. So let's see what that does. All right, now we got something to work with. So if, for example, we decided to say, let's say which p-values are less than 0.1. So at a false discovery rate of 10%, what do we get? Well, we get 1, 2, 3, 4, 5, 6, 7, 8 rejections, 6 of which are true positives and 2 of which are false positives. So, okay, it's more like 25% false positives, or false discoveries, I should say. 25% false discoveries instead of the desired 10%. But again, presumably, if we were to do this over and over again, we would get on average about 10% false discoveries. And you can change that threshold too. If you want 20, we say, wow, now we have a lot. I don't know, so many that I don't really want to count them all. So we'll just sum it and get 34 rejections. That's kind of neat. And it looks like most of them, well, how many false ones do we get? 1, 2, 3, 4, 5, 6, 7. So 7 out of 34 are false, which is about 1/5, slightly less. So again, yeah, just a little bit above 20% there. So actually, we did a pretty good job with that one. I like that. The target false discovery rate was 20%, and the achieved false discovery rate or false discovery proportion that we saw was just a hair above 20%. So that's kind of neat. I like that. That gives you an idea of how these methods work. Before we're done, we might as well try the BY method just to see how it compares. Last time it set everything to be 1. Let's see if it can do better this time. Okay, it's still super conservative, but it didn't set everything to be 1. Again, we actually are in the case that all of these p-values are independent because I generated them to be independent. So this method will be overly conservative because it is not accounting for the independence that I know is in the p-values. In this case, yeah, we don't get very many rejections. But at least you can kind of get an idea of how these work in practice. So again, p-adjust function allows you to adjust a collection of p-values. What you do is you use the method you want, you set a threshold, whatever you want it to be, and you say how many p-values after being adjusted fall below that threshold. Those are the ones we reject. And whether you're doing FWER or FDR control, the interpretation of those rejected p-values will be a little bit different. We either have the probability that any of them, at least one is a false positive, versus the fraction of them that we expect to be false positives. And it's really good to remember what the differences are between those two methods, because they're also just really important, and you might have to use them in the future, not even with design of experiments, but in other things. If you're doing regression, if you're doing, I don't know, time series, if you're doing really anything in statistics, you're probably going to have p-values, and you're going to want to adjust for multiple testing. Right, so that's a lot for today. We're done with multiple testing. This is just the quick little 2 lectures, about 3 hours of notes, and we're going to be moving into factorial designs, but that will be in the next lecture. So see you there.